Hello and welcome to day 17 of Advent of Code, the Digging Out of the Snow edition. After yesterday's, a footish of snow dropped down on New York City, excited to get back into things. It's a little bit late on the streaming side, but we'll get it done. I'll switch over to the desktop. We'll start day 17. We'll start the timer. I already got the code kind of lined up as usual, so let's click right into it. Short and sweet on the intro today. As your flight slowly drifts through the sky, what kind of flight is this that drifts through? Am I on a hot air balloon? The elves at the Mythical Information Bureau at the North Pole contact you. You know, it's the in-flight Wi-Fi, right? They'd like some help debugging a malfunctioning experimental energy source aboard one of their super secret imaging satellites. The experimental energy source is based on cutting-edge technology, a set of Conway tubes, that's a nice Conway reference, contained in a pocket dimension, okay? When you hear it's having problems, you can't help but agree to take a look. Oh, so it's called Conway tubes. Oh boy, so it's Game of Life references there. The pocket dimension contains an infinite 3D grid at every integer 3D coordinate XYZ. There's a single cube which is either active or inactive. I wonder what the size of this cube is and which corner. In the initial state of this pocket dimension, all cubes start inactive. Well, almost all cubes start inactive. The only exception is a small flat region of cubes, your puzzle input. The cubes in this region start in the specified active or inactive state. Oh boy, this is going to be 3D Conway's Game of Life. The energy source then proceeds to boot up by executing 6 cycles. Each cube only ever considers its neighbors, any of the 26 other cubes where any of their coordinates differ by at most 1. Given the cube at 1, 2, 3, the neighbors include the cube at 2, 2, 2, cube at 0, 2, 3, and so on. During a cycle, all cubes simultaneously change their state according to the following rules. If a cube is active and exactly 2 or 3 neighbors are also active, it remains active. Yeah, this is 3D Conway. All right. The engineers responsible for this experimental energy source would like to simulate the pocket dimension, determine the configuration of cubes should be at the end of the 6-cycle boot process. Consider the following initial state. This initial state represents a small 2D slice of it. In particular, this initial state defines a 3x3x1 region. Simulating a few cycles produces the following configurations, where the result of each cycle is shown layer by layer at each given z coordinate, and the frame of view follows the active cells in each cycle. Frame of view follows the active cells in each cycle. Which one is active? The hashes, and the dots are inactive. So if these active ones, z equals 0, right, and then after one cycle, okay, interesting. So it goes out, right, because as things get bigger, how many cubes are left after the 6th cycle? So our configuration looks like that. We'll go over to PyCharm, we'll put in our main input. I do want to capture our demo input. So one thing that's interesting here is, like it said, it's an infinite grid. So it has some interesting implications in terms of storage of the data format. Yeah. So I'm inclined to potentially go with a dictionary here rather than trying to actually map out the full space, because I know what all the neighboring coordinates are, and so I can find its neighbors. Yeah, let's try it this way, and oh, excuse me. We'll see how it goes. All right. We're going to parse our file. This is going to be similar parsing as before from when we saw this, but Let's do line by line, strip the line, grab the coordinates. We want inactives. Do we want to capture? We only care about active, I think. And how do we want to set the coordinate grid? That's the other big question. Let's do row column grid still. So this one is 0, 0. 0 because of Z. Don't forget Z. And so for each line that comes in, we actually don't know. Like what I want is for each, because it'll come back as a list of lists. So let's return a list of, should we return a list of the actual coordinates or a list of the characters? Part of me wants to return a list of just like the coordinates that they are, but it won't work because I don't have the Z, the row number. So for a given line, let's just do a find all the indices that are active. How about that? So we'll do line.find. We'll find this. It's almost easier to do it with just a straight search, linear search. For character in line, if C is the hash, then we note its location. So let's do enumerate line I comma C, and so then we have its index. So we say active locations dot append the index. We'll define it here and we'll return it here. And so we'll get back a list of lists of the row numbers. So we'll have then, yeah, that works. And then for row in lines, we'll have a list, right? So inside of this list, R is a list, it's a row. And so the X coordinate, right? Each one for X in row, we have a bunch of X coordinates of the indices on which it was. And then we want also the not just the X coordinate, right? Not just but also that I value too, the Y, I guess, value. Am I getting this backwards? Yeah, I am. So it should be I and J. And so this is kind of its horizontal position, which is, it's which column it's on. So, it's I, J, 0 is the coordinate triplet that the value falls on, right? Because it's I and then J, and then then we can add it to our little map. So we can say active map, and we can say active map dot, at this location is, let's just say 1, just to allow us to turn things off and potentially return a 0. Yeah, and then later when we get ones that are inactive, if they're not there, we return a 0. If they are there and it's 0, it's still a 0. Right, so this is active. And let's return active map so we can just check things here. We have this little spacing issue again, it looks like. Okay. So what we're expecting to see is at position 0, 1, that's there. At position 1, 2, yep. Position 2, 0, 2, 1, and 2, 2. Great. So I never converted these numbers to an integer. Oh, it's fine, right, because we were appending the numbers. So we already are out of the hashtag game. So now we need a way to retrieve the relative coordinates given a set of x, y, z. So I want to write a quick little function here. Def neighbors, get neighbors of x, y, z. And this, I want to return that list of 26 possible values. So we're going to do it right this time. Because last time I did not do it right. Deltas is -1, 0, 1. And we want 26 values. The only time we don't want to get it back is when x, y, and z are all 0. So for I in deltas, for j in deltas, and for z in deltas, so we do every combination of these things. So it would be 3 times 3 times 3. If not z in deltas, I, j, k. If I is 0 and j is 0 and k is 0, then we continue. Otherwise, we're going to take x plus I, y plus j, z plus k. So that's our kind of, that's the next value in this kind of set of neighbors. So we'll say neighbors is a list. And so we can do n.append this whole thing. So we have a list of tuples. So we shouldn't need to change that. And then when we're done, we can return n. And so let's check that. Let's say we, for this and that, that equals j, j equals active. Sure, let's try to get neighbors. Let's just test out get neighbors for cell in active map. What do they call this? Cube. We'll use their nomenclature for cube in active map. And we should say cube active in active map dot items. If active, then we do get neighbor of cubes. Apparently I can't spell neighbors without this thing yelling at me. Let's just print neighbors. So get neighbors of cube. Cube should be key, which is this whole thing. Active map at a certain position. Maybe I need this to be more explicitly tupleized. Get neighbors is missing. Oh, it's because this unpacks it. Yeah, that's true. I think you can do this though. Just hey, there it is. That was fun. So what am I doing here? All right, I want to split by new line so I can see them all. So the first one we're doing is 0, 1, 0. So we're checking the neighbors at all of these positions. All right, 0. There's no good systematic way to check if I'm doing this right though. Well, we can at least check this. Assert length of n equals 26. So that's good. And let's try calling a one-off. Instead of doing all of this and printing that, let's do get neighbors of 0, 0, 0. And print. And so we're expecting to see from -1, and then this goes 0 and +1. And then we do -1 on y, with -1, 0, +1, and then +1 on y with -1, 0, and +1, and then 0 on -1, 0, and 1, and then 0 on 0, -1, and 1, and then 0 and 1 on -1, 0, and 1, and then 1 on -1, 1, -1, 0, -1, 1, then 1, 0, then the triplet, and then finally 1, 1, -1, 0, 1. Great. So feeling good about that. And so then what do? We say for each of these neighbors, we want to count up how many are active, right? So we say get active n for x, y, and z. Def. So if it's active and exactly, let's just say get next state. Ooh, but if a cube is inactive, but exactly 3 of its neighbors are active, the cube becomes active. So we need to find the largest values, like we need to check the values around each of the active things too, that could possibly be touching our existing cubes that are active. So this is good for a existing active cube, and we can find out if it remains active. Yeah. So it's more that it's saying next state of this given a mapping. And let's wrap this up. I know the syntax is gonna be funky. Okay, so x, y, z equals cube. Get neighbors of x, y, and z. Oh, yeah, I could have just done the same thing I did before. Okay, so we get the neighbors, so that's neighbors. We'll just call it nay. Nay. If exactly 2 or exactly 3 neighbors are also active. So we got the list of neighbors. So for n in neighbors, we need to find out if active map dot get n, comma 0 are active. And so this will accumulate to active count, which will be saved to here, plus equals. So we'll get either 0 if it's 0, or not if it's not. If active count is exactly 2 or active count is exactly 3, then return 1. That's the next state. Else return 0. And I spelled return wrong. Okay. So that's great for when it's active. But if a cube is inactive currently, but exactly 3 neighbors are active, the cube becomes active. So given a position, it does matter if it's active or not. Okay. So we have a cube, the active map, and whether or not it is currently active. Sure. Because we could look it up in the active map is the thing. We could do this on cube itself. So we can say is active equals active map dot get on cube. Yeah, might as well do that. And so now we know if the value itself is active. So if is active, then we do that. Else is not active, then exactly 3 neighbors are active. So that's this part. Else, if exactly 3 neighbors are active, return 1. Else return 0. Remains inactive. If it's active, then it remains active. Okay. It's verbose, but it's clear. So let's test this now. Next state. We have get neighbors, so instead now we're going to say next state. Takes two position arguments, but three are given. Indeed. It's unfortunate I have to pass the active map around just because, like, you know, it would be nice to have this in a class basically and just be able to say like get next and then have it handle it. I think perhaps traditionally I would have done it that way. So in this example, before any cycles, it's like this. After one cycle, let's try to get the new updated state for its own kind of original starting point, right? Oh, I did that, I guess. No, I didn't. So this is 0, 0, 0. After one cycle, it's saying that this should be active? Why would that be? Exactly 3 neighbors are active. It itself becomes active. Let's review. Active is a hash, inactive is a dot. Active is a hash, inactive is a dot. My main problem is that at z equals 0, it's a dot in this first position. Why did it become active after one cycle? So even though the pocket dimensional 3 by 3 by 1 region. So let's consider this one. This one has 2 neighbors who are active, and so it's going to become it's still inactive. But here it thinks it's active. See, this is what I'm talking about. I'm not understanding this correctly. So before any cycles, it's like this. And after one cycle, well, let's look at this middle one, right? This middle one clearly has lots of values around it. And so it should stay inactive. But it actually becomes active. Man, what am I feel like I'm misunderstanding what it's saying here. Single cube, either active or inactive. Active is hash. If a cube is active and 2 or 3 are also active, it remains active. Otherwise, it turns off. If it's inactive, it's a dot, and exactly 2, 3 are active, it also becomes active. Simulates the following configurations where the result of each cycle is shown layer by layer at each given z coordinate, and the frame of view follows the active cells in each cycle. So if it's currently, what's surprising to me is that this cell in this upper left corner became active because it is not surrounded by a bunch of active cells, right? It is inactive, a dot, and then becomes active suddenly across all 3 z values. You see that? This is a hash, which as long as I keep going back up here because I keep thinking, did I mix it up or something? But active is a hash, inactive is a dot. And the only way, and so it's inactive, it's a dot initially, right? This upper left corner piece. And so if an inactive one has exactly 3 active neighbors, it becomes active. Am I treating the neighbors wrong? Coordinates differ at most 1, 1, 2, 3, 2, 2, 2. It seems right. The engineers responsible would like to simulate the pocket dimension to determine which configuration of cubes should be at the end of the 6-cycle boot process. Before any cycles, after 1 cycle, this initial state represents a small 2D slice of it, a 3 by 3 by 1 region. Is it saying that the slice is like the whole grid is like that? At every integer 3D coordinate, a single cube is either active or inactive. In the initial state, all cubes start inactive, almost. The exception is a small region of cubes that start active. The energy source executes 6 cycles. Each cube only considers its neighbors. During the cycle, all cubes simultaneously change their state. Yes. So what about this one here? This one is active. It has 1, 2, 3 active neighbors. And we're not counting itself. And so something that is active and has 3 active neighbors, the cube should remain active. So it does across all 3 kind of dimensions or sides, which is weird. All right, let's just try running it with the visualization. I'm going to add a visualization here so we can like really directly compare. Because clearly I'm missing something. I think the code is solid, so let's run the piece and see how it does. So we want to get, so the current, and I'm going to need to know current map dimensions, so to speak. Like we'll grow the map dimensions as we go, as the map values kind of increase, but hopefully this approach works. So we have active map members, get neighbors. So this is all reading in, and then we want to go through the full space, checking for the next state of each cell cube and updating the new active map with it. So let's see, new active map, new map. And so we want to say for I'm also trying to figure out what the range of X, Y's, and Z's we should be checking. For now, we can do kind of for dims is -1, 0, 1, because we know that's all we're going to have. But later we should check more things. For I in dims, for j in dims, for k in dims. So we're going to check the full space, I comma j comma k. We want to get the next state of that. Next state active map. And so then we'll say new map at ijk equals this next state. Yeah. I'm reasonably happy with that. Printing it gets a little bit dicey. Display map, new map. So let's define this. So we want to show the full kind of space. Again, we'll hard code some values for now while I kind of defer trying to come up with how what we should do about that. For k in dims, for I in dims, for j in dims. So I'm switching up the order so I can display it the way they have here in this here. So we'll say z equals print, so he's typing 4. Z equals k, and then we'll print the value if the value in map at ijk, no, it should be map.get. It's this thing. If that value is 1, then we're going to print and equals quote quote. We're going to print a hash, else print a dot and equals quote quote. And then at the end of this for loop, we just print a new line. Yeah, let's see how that looks. I think this will work. Expected for, I got another. Yeah, get that. Great. So definitely did not do a good job there. Put that here. And then what do we got? Okay. It kind of works. Let's put a little new line here. All right. More to the point, however, this looks very different from what we started with. So if we were to print our original map, right, we made this whole thing. So display map of our active map up here. Well, my first concern is that only this is turned on. So that's not great. What's up with that? I think it's because we're not looking at the right region of the map. Our map contains values of 0, 1, and 2. All right, so our dimensions are off. That'll do it. And change here. Not my best reusable code, etc. day, but you know, you take what you get. So this is our input, supposedly. Hash, blah, blah, hash, triple, blah. Okay, so that's there. And then we've got nothing above and below it. Oh, and then, maybe we should have a -1. Okay. So we started off, it's here. And then 0, 1, 2. And then we have this sort of thing, which, not exactly what we're looking for. Which again, I don't understand what I'm doing wrong here. If inactive with exactly 3 active neighbors, the cube becomes active. Otherwise, it remains inactive. And it says that it does the thing simultaneously. This initial state represents a small 2D slice. This state defines a 3x3 region where the result of each cycle is shown layer by layer at each given z coordinate and the frame of view. Like almost all are inactive, aka a dot, and things become active. And so the only way they can become active is when exactly 2 or 3 of the nearby cells, like this is the thing, it doesn't add up. Perhaps it's like a frame of view problem. That's possible. So let's draw this out then. So I'm gonna take this. I'm gonna go into our scratch sheet here, and just delete all that. And that did not work at all. That is marginally better, but still not really what I'm trying to do. I'm just gonna move this over. So we want this to be 1. Let's just highlight this, and there we go. And make this middle, and make this a little bit wider. That didn't work at all. Okay. Fine. 0, 1, 0, 0, 0, 1, 1, 1, 1. So that is going to become, this one's inactive, it has no neighbors, so it stays inactive. This one is active, it has only 1 active neighbor, so it dies. This one, actually, yeah, I shouldn't be looking at that, I'll throw it off. This one is inactive, it has 2 active neighbors, so it stays dead. This one is inactive, and it has 1, 2, 3 neighbors, so it lights up. This one has 1, 2, 3, 4, 5, too many neighbors, it stays down. This one has 1, 2, 3 neighbors, so it stays up. And this one has 1 active neighbor, so it goes away. This one has 1, 2, 3 neighbors, so it stays up. This one has 2 neighbors, so it goes down. And so now the question is, we can also check these values, right? So this one has 1 active neighbor, so it stays down. This one has 2 active neighbors, so it is also nothing. This is also nothing. Now coming across the bottom here, this one has 2 active neighbors, so it stays down. Whoa, that was weird. It's giant. This one has 2 active neighbors. There we go. And then here, this has 3 active neighbors, so it wakes up. This one also has just 2 active neighbors, so it goes down. So what's interesting here now is, should I also be considering like the rows on the above and to the left of this? Like, should this whole thing be moved over and down 1? So that now I'm here, and I'm thinking, what are these? Still 1, so it stays 0. Right? And this one is still 0. This one, still 0. For whatever reason, it decided to be formatted weird. Okay, then this one, it is still 0. I think, yeah, these are all still going to be 0. So at least that part wasn't odd. But take a look. Originally, we had these positions, right? And this is centered. And it's like we have this extra 1 down here, and this row is zeros. So it's sort of like we moved from having these be bolded to these be bolded in the kind of layer that we've moved to. So -1, 0, 1, 2, -1, 0. So here we see that we have those two, this one and this one, and then we have just that one. For some reason, my thing seems to think that there should be an active. Oh, right, because if it's active and there's 2 or 3 around, it stays active. Whoops. So this, if there's 2 or 3, so this stays active. So I'm looking at this slice here when I'm just displaying these two, right? And these two and these two. And what's cool is like, because I did do -1, so like -1 is over here. So we're like, we can extend in both directions indefinitely. So I should be able to do kind of, this is the original 9. And I should be able to get that extra 1 to show up if I now display. I know we're kind of doing some wonkiness here. Let's add a 3 here. And so now we start out like this, and then yeah, it's not finding it. That's a little bit concerning. We're not introducing this one here, where it used to be off. Now it's on. Is active. If it's inactive and there's exactly an active count of 3, so that's assuming my active map dot get. Oh, active count. So that just gets the true false state. I don't think that this is right. Oh, no, this is right. This is just getting is active of the certain one that we're on. And so if it's not active, the inactive, oh, right, and our active count is being computed up here. For each of the neighbors, we're grabbing the value. And are we doing the neighbors correctly? Yeah, that looks fine. So we got the neighbors, we go through each neighbor, we see if it's in the map, and if they're not in the map, then they are not active. So what is happening when we get to this position, which is 0, 1, 2, 3. 3 rows down, 1, 0, 3, 1, 0. And 3, 1. So z equals 0, and then it's 0, 1, 2, 3. -1, 0, 1. Yeah, 3, 1, 0. Let's try to debug that by printing out a specific, let's get the count, active count, if, what are we on? Cube equals 310, print active count. We could probably just get the map directly, but 310. So let's find that in our little hodgepodge here. Oh, we never got to it. We never checked the state of 310. Next state being called here for 0, 1, 2. Ah, yes. Because we're only going through 0, 1, 2. We're only going through these 9. We need to look a little bit further. On both directions, it appears. So it's like -1 and 3. So we have to something to keep in mind as we go is we need to extend dimensions by 1 bigger than it used to be every time. So yeah, there's 3 neighbors, and we're going from here to that. So at z equals 0, we have every other, the last 2, and the middle. At z equals 0, every other, those 2, and the middle. All right, so that's how it's being done. And then z at -1, we have those 3, like that. Is the frame of reference staying constant though? It is, right? Like it's moving down, but it's all moving down together. And -1 is the +1 is there. Okay, so that is the thing that we are missing. How do we ensure that we get a big enough view, especially on a thing that's, how big is this? 8 by 8 is the final thing. And like as we evolve this, right? If we don't display the old map, the original map, this one. So this is loading it. This is the new map. This grabs the next state. And then, so let's roll this into another function. For if it's active, neighbors get, like next state takes care of getting the neighbors and all that, right? Next state. Yeah, this next state is a single cube's next state. And then we have some code here that takes care of getting the entire next map's next state. And then down here, we're saying if a cube is active, we wanted the neighbors. That was just for testing, so we don't care about this anymore. Well, let's just comment it out for now. Maybe the code will be useful. And I'm going to take this bit here, this little ditty, and put it in, I'm going to cut it out and put it here. Next map. Don't know what arguments I want just yet. I don't care about passing in the old map. Well, I do, old map, because I need to go through it. So that's this one. And our new map is here, and so at some point we're going to return the new map. Now the dimensions, this is where it's interesting. If we go through where the biggest and smallest values of all the different values inside are, right? So what I want is I have this map of active values. I want to have the cube that surrounds them, and then +1 above, below, and around it all. So let's first talk about finding the max and min of all the x's, all the y's, and all the z's. So I have this thing, and if I want to get without, I'm trying to think if there's a clean way to do this. There might not be. So if I say max x, like min x, max x, I'll just call it x range. And then what do you put here, right? Like the initial values. What do you put for those initial values? So, all right. So negative inf and positive inf. Don't know if inf works directly. Yeah, I didn't think so. Small, float, negative inf, -1 times and big. So let's do it that way. And oh, actually, let's just have a variable called inf. Hey, that takes care of it. Range, and then we'll do one of each of these. I got these backwards, right? Yeah, I did. And we're starting at 0. And so we'll only want to go down. All right, never mind. We can just do this. I think we can just do this because we're starting from, like, we have that base state of 0, 1, 2. Like, it should only go up from here. So this is a pretty reasonable starting point. For, I don't really care about the keys. I only want the values. Yeah. And then so I can say for x, y, z in old map dot values. Wait, did I say values? I meant keys. For each of these keys, regardless if they're on or off. Ooh, it does matter. Items. Okay, so it's these three, comma, active. If active, right? Only if it's active will we really care about it in terms of the dimensions of our map. We want the x range at 0, the min, to be the smaller of all of the x's, the smallest of all the x's. So of x, between x and x range at 0, whichever one is smaller is the one we want to keep. And similarly with x range at 1, but with max, whichever one is bigger, we want to keep that. And so I think we can do that for all of this. If I can keep my keys straight here. And changing all of these two to a y, these two to a z, changing these two to a y, changing these two to a z. So that'll go through all the things, reset the values, so then we'll have proper x and y ranges. And so then we can say for I in x in range of, I mean, those two ranges basically. And if we just add 1 to whatever the maximum is, right, at any time, that'll take care of that problem. The question is, can I pass a range, a thing like this? Okay. Haha! That'll do it. It'll unpack it like that. I love it. All right. So we'll do that. Range for each of these ranges, but we'll change the variables. All right. So that should go through all of our, what was this supposed to do? Get the next map. Oh, it does get the next map. Okay. And then we'll deal with this display problem. Maybe we should, let's make a new function to determine these maxes and mins, because it looks like it's useful in a couple of spots. So get that out of here. Let's call it max window, max range, map dims. Yeah. Map dims of old map is x range, y range, and z range. So we returned a tuple of the various ranges. Def, map, dims, old map, we call it, just because that's what our code already uses. Actually, it doesn't matter, does it? So it only shows up this one time. So we'll just put it there and return this tuple. And so now in display map, instead of this mess, we can call map dims properly and do the X range thing. So let's just get this line. Display map, we want that. For K in range of our Z range, let's grab that. That's this one, right? For X in, what am I doing here? All right, for X in range, X range, I in that range, X range, and then J in range, Y range. Everything else remains the same. Let's try it. Make sure things are displaying. Nothing is displaying. That's how you know things are working, when nothing is working. Cool. I guess I don't need dims anymore. And map dims, return the thing. Next map. It took away a lot of the prints, that's why. So now we want to do next map of old map. Oh, there's no old map. It's called active map. And our new map is going to be also, funnily enough, called active map. So we're just going to get the next map, right? And so for in range 6, we will get the active map 6 times. At the end of which we'll have whatever we have, and we'll sum up all the values that are 1. Active map dot values sum. Indeed, old map is not defined. Map dims. Oh, I didn't realize I made that M. Go figure. I got 24. What does it think? 112. Great. Simulate 6 cycles. Huh. Can't say we didn't try. Wow, this thing ballooned out to 26? That is a lot. Alright, let's scroll here. What's most disconcerting is that we have a bunch of blanks. Everything is blank. Also, why is this showing such a giant thing? Alright, we're definitely doing this wrong. This dimension finding. Made some mistakes in this dimension ranging, didn't I? So map dims, when we try to get the next map, slash when we try to display the map. Where are we going with this here? Print next state. Active map. Okay, let's not deal with that just yet. Where are we printing? Oh, we display the new map every time we get the next, we get to the next map. Okay, so for starters, I want to check our ranges. So print X range, Y range, Z range. So initially we have 0 and 7. So that is definitely wrong. Why are they all the same? And why is it 7? So the max is of each of the items, key active items, if it's active, print the map. Let's reduce this range real quick to 1 for now. So I'm saying it is 0, 2. And so for each of these things, it's going through and it's like, if it's active, X range is the smaller of either the value of X or the current stored that. Great. Here, then we say X is it because of it's probably because of the +1. Well, no, it's outside of the max call. So the max of whatever X is still X. So then when we get to like something like this where X is 2, and then X range at 1, it still shouldn't be doing that. That's so odd. So it's calling map dims. We're getting these terrible ranges, and this is like kind of not even relevant to the our problem in some ways here, right? 1, 2, 3, 4, 5. It is suspicious though that there are 5 elements, and we end up with 2 plus 5 on X, Y, and Z. So it's like each time we're storing the value of the max value, we're always adding 1 no matter what. Okay, yeah, that's not great. Now I'm concerned that it's going to come back 0, 2, but then not display properly because of the way range will unpack that. This is not cool. All right, we'll do it the old school way, I guess. 0, at 1 plus equal 1. Yeah, something like that, because we have to offset by 1 just for the sake of ranging. And so it's like 0 to 3 exclusive, yeah. And then we have 6 for some reason. What's the number 6? I think that's just saying that there are 6 active. Well, problem is there's 1, 2, 3, 4, 5 active. So, missed the boat on that one. And after 1 cycle, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 active. So that's not right either. All right, let's display this map after 1 cycle. But hey, at least I'm, displaying the right ones, kind of. Oh, kind of. Not the right ones. So we see here we have values at coordinates. Ooh, we don't have values at some of these coordinates. Oh, and when it comes back and gets the next state, if the next state is 0, let's not insert it. There's just no need. If next val, yeah, because if there's nothing there, there's nothing there. It's not going to print it anyway. Like, it'll just make it a lot easier to read these printouts. The big concern here is that we're not iterating. Oh, right. We're not iterating around it. the dimensions. We have to go one more than the ones that we're giving. So let's say map dims, and then we'll say expand equals false by default for printing reasons, right? But if expand equals true, we're going to boost the values once more, right? So if expand, then we'll do x range at 0 plus equals 1, x range at 1 plus equals 1. I know this is just, there's got to be a better way to do this, I feel like. So I'll be curious to see how others went about kind of encoding some of this information. Still says 6 because I never called expand. So let's see here. This is next map, get our range. We say expand equals true. Now it prints out 2. What does that even mean? Our range is now 1 to 4. And our dictionary has shrunk. Oh, wow, it has shrunk a lot. What did I just do? Ah, the lower value needs to be -1. Subtle bugs are subtle. Now we're up to 11. Overshoot, undershoot, overshoot, undershoot. And yeah, I can get rid of that 0, 1, 3. Yeah, this little debug thing was, while a fun experiment, not necessary. -1 to 4 was our ranges to check, to look at, or that we returned, but which time? Next map, get the thing. So this is the expanded ranges. So instead of 0 to 3, going -1 to 4, aka -1 to +3 inclusive. And so that should allow us to see if we can't get this one to show up right here. This position, right? This is 0, 1. This is 0, 1, 2, 3. So 3, 1 again. Showing up and messing us up a little bit here. 3, 1, 0 is there. So we got that going for us, which is nice. We are printing stuff. So let's take a look at what we're printing now. After that first iteration, we're expecting to see after one cycle these 3. So we had this working before, so it should still be working in theory. And those 3. So why is our total 11? 1, 2, 3. Did I just count it wrong? It's possible. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I just counted wrong. It is 11. That is great. So we got one cycle down. Let's go for cycle number 2. Range 2. So here's our second cycle and its corresponding display. So we're now, the ranges are starting to change it up. So I'm really glad we did those calculations. We have one value in the center of -2. That's good. All right. -1, we have 1, 2, 1, 1. 1, 2, 1, 1. Then at 0, we have this clump of 5, and then these 4 with a hole. Clump of 5, these 4 with a hole. At 1, we have 1, those 2, that 1, and that 1. And then back to 2 again, we have this one. It's symmetric, which is kind of cool. Let's do 3 cycles. Let's just jump to 6 now and see how we did. And it says 112. It does say 112. All right. Let's do the big kahuna. Let me just clean up a little bit on the display side of things. This seems fine to show our map each time, even though it really probably doesn't help kind of you know, it doesn't really help with the whole, where is the print? wouldn't help us debug. I'm not sure where here's the map I'm printing. Okay, cool. So let's change where is our file name? Here it is. Run it again, 242. Kaboom, ka-ching. All right, there's one down. On to part 2. Wow, that took an hour. Oh, that's brutal. Wow. I don't know. Okay. And let's see what part 2 brings us. Oh, you gotta be kidding me. The pocket dimension actually contains 4 spatial dimensions, not 3. Oh, we're gonna have to rework all the code. The pocket dimension contains infinite 4D grid. Every dimension exists single cube, really a hypercube. Each cube only ever considers its neighbors. Any of the 80 other cubes where the differ by at most 1. The initial state of the pocket dimension still consists of a small flat region of cubes. Furthermore, the same rules still apply. Consider the number of active neighbors. All right, so it extends by dimension, but it's not terrible. They haven't made it insane. Consider the same initial state as the example above. Even though the pocket dimension is 4D, this initial state still represents a small 2D slice. Simulating a few cycles where the result is shown layer by layer. And we got all of these combinations. We have these cubes in active state. Simulate 6 cycles in a 4D space. How many hypercubes are left? All right, I think we're in pretty good shape. I mostly just want to copy some of the existing work we have and make a few tweaks for kind of the part 2 implementation. So we'll still use the same parser. Did I do anything in the parser? I don't even remember. It's been so long ago. Okay, so we do have a parse that we'll need to use. So let's keep it up to the parser, down to the return, like that, and something like that. Okay, and then now we have to start shifting things over to the 4D implementations of these calls. So cleaning up some comments here. Basically just have to hope it works. Oh, actually, you know what? I think we do need a new parsing. Well, do we? Yeah, we kind of do. Well, no, it's here. It's here. We parsed this is where things get crazy. So let's do it. Part 1. No, not part 1. Part 2. We have W. No, that's not a W. That's a O. I, J, K. What comes after K? H, I, J, K, L. So it's L and W are our variables for tracking the dimension and for looping on it. And then we have next map is the next thing we need to, and then next map will call, next map calls map dims, calls display map, and next state and neighbors. Okay, so we got a couple of functions to handle here. I'm just gonna grab all of this, shrink that, and put this here, and it's gonna complain. I'm gonna switch over to where's the view that shows us the structure? Here we go. So here's our get neighbors, next state, display map, map dims, next map. So those are all from part 1. I'm shrinking them off so I don't accidentally scroll up to them and use them. So we'll keep the parse 1. I think that's still good. This still, okay, now we're starting to see where things break because I added that 4th element. Things won't unpack properly, etc., etc. Good. And I'll just drop the day 1 run command because I don't need it. And I can drop parse line as well. All right, so let's call this, just put a 2 after everything. All right, so next state is 2, display map 2, dims 2, next map 2, and part 2. And then when we call, we're going to call, just go through this carefully here. Next map 2, active map.values. Okay, that's all good. So now we're up to next map 2. Next map 2 starts out, this is a useless variable, right? Yep. So it doesn't care about that. It starts out, we're going to call mapdims2 to get not just X, Y, and Z range, but also W range, passing in this old map. And then if we need to print later, we need to print a W range. We need to go and get indent everything. We're going to have this W range, and we're going to, for L in W range, and we're going to get the next state at L. And we're going to get next state 2. Next value is here. We're going to index into the map at L and get the next value and write it in. So next state and mapdims2 are the things we got to work on. So let's do mapdims. Where do we call display map to? I guess we don't really have to change it if we don't end up calling it later. It just works. Let's paste this in here. W range starts there. We'll have a Z, and we'll do min max on W range, W range, W range for X, Y, Z, W in map.items, X, Y, Z, 0, 1, 0, 1, 0, 1. We'll have a W range here. If we expand, we're going to need another W range there. And we're going to need to return W range. All right, good editing, careful editing, but going well so far. W range. What order to show this in? It looks like we're going by, let's see here, Z equals 0, and then after one cycle it's at W is -1, and then at W is 0. So W is outside of the Z loop. Whoosh. Alright, so it goes. That's how the cookie crumbles. Okay, L at range, W range. This whole thing goes in 1 and print Z equals blah space comma. So Z equals blah comma W equals L. And that's the change. We're still printing a 2D thing. Here needs to be L. And we're going through W range. We've got the L, we've got the X. Okay, I think that's display map 2. Next state 2. We've got our queues, we've got the neighbors unpacked. Ooh, the unpacking is a huge save for us. This is really useless now. We get the active neighbors. Yeah, that's still fine. If the count is 3, does next state not change? That is wild. All right, let's get the neighbors. Let's get the neighbors. X, Y, Z, W. Where do we call get neighbors? I mean, I know we call it, right? I think. I mean, we have to, right? Because we need to, yeah, get neighbors. Oh, I need to update this. Get neighbors 2. Make sure I don't have any other calls here. This is on the map. So easy to miss something here, and it'll be terrible to debug. The deltas don't change, but we do need a extra loop in here for L in each of our deltas. If and W, no, L equals 0. Continue. Append W plus L. assert that the length now is 87. What was it? Each of the 80, yeah, 80, because it's 80. Yeah, 3 to the 4th minus 1. Let's just write that out. 3 to the 4th minus 1. I think we might be done, folks. Prepare for the onslaught of errors due to shoddy editing. Crunch, 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 crunch. Wow. Okay. I can't not put the number in because we got a number. We owe it to ourselves to try it. And it's good. All right. That is amazing. 1 hour and 10 minutes. So 10 minutes later, we were able to wrap this bad boy up. That's real solid. So, I think I got kind of lucky with the way I wrote the code a little bit. Like, I could have made classes and stuff. I'm not sure if that would have made it any easier. I probably still would have had to go through and edit everything, and I probably had to duplicate the class for a 4D arrangement. I wasn't really dynamically considering the 3 dimensions. They were very kind of hard-coded, and there were a lot of manual adjustments we had to make. But organizationally, the code probably could have been easier as classes. Maybe. What else? Overall, we kind of methodically, I liked what we did with the get neighbors, and figuring out this display problem was a real trick, right? Like, going through this and realizing that these numbers kind of start floating off on you was tricky, and I suspect there's a good way to do this so that we didn't have to print all the extra zeros around it. I guess in a way we did that with the dims. We found the kind of tightest bounding box, because it probably would get quite large after a while. Yeah, so hope that was interesting. Day 17 in the books. Conway's dimensions, dimensional tubes, let's call it. And hope that was interesting and useful. 8 more days to go till the end of this epic journey, and we'll catch you tomorrow. And until then, be safe and don't freeze if you're on the East Coast with all the snow coming down. Stay out of those puddles. They are cold and they will get you. And we'll see you next time.